Let's take a look at logarithmic functions. Now, you may be looking at this graph that you can see right here and saying that is an exponential function. It's an exponential graph. The function that I'm looking at is exponential, and you're absolutely right. It is. This is an exponential function and the graph of an exponential function. What we want to notice about this graph is that exponential functions are one-to-one. They pass the horizontal line tests. Any horizontal line that I draw on there goes through there one time and only one time. It's one-to-one, which tells me it has an inverse. And we don't have to do anything fancy. We don't have to restrict domains or anything like that. Exponential functions are one-to-one just as they are, and so they have inverses. A logarithmic function we're going to define as the inverse of an exponential function with the same base. So here comes a sentence. The exponential function with base A, and I'm not being specific here, so A can be anything as long as it's positive and not 1. Could be more than 1, less than 1, could be E. The exponential function with base A has an inverse, since it's one-to-one. And we're going to define that inverse of the exponential function with base A as the logarithmic function with base A. I'm going to write it like this. I'm going to write log base A, and if you're looking at this printed in a book, that's like a subscript. Log base A of x equals y. A, I called the base, so there's my base. Y is the exponent that I have to put on the base in order to have a result of x. Well, we already know something that works like that. It goes like this. The base is A. Y is the exponent that I have to put on A in order to get x. These two statements give exactly the same information. It's in a little bit different place. We have the base of A, the base of A. We have the exponent, y, the exponent, y, and this third number that I don't have a great name for. I've heard it called the argument of the logarithmic function, so I might use that sometimes, but this third number, x. So these two statements give exactly the same information. They just do it in a slightly different way. Y is the exponent that we put on the base of A in order to get x. What this does for us is this says any logarithmic statement like this, I can rewrite in exponential form. It's like rearranging the furniture in the room. All the same stuff is still there. We're just going to put it in a little bit different place. We can go the other way too. Any exponential function, I can rearrange into a logarithmic statement that gives all the same information. So let's look at doing that. If I have the statement 3 to the 4th power equals 81, I can rearrange that into a logarithmic statement. So I'm going to write log, the base in the exponential function is here. So that's the base of my logarithm, log base 3. The exponent in my logarithmic statement goes over here. So I got the base, I got the exponent, and then I have this third number here, 81, that becomes the argument of the logarithmic statement. These two give exactly the same information. 3 to the 4th power equals 81. Log base 3 of 81 equals 4. It just looks a little bit different. Everything's in a little bit different place, but they mean the same thing. Give the next one a try. Pause for a second. See if you can do it. And I'll do it. We'll make sure we got the same thing. So I have 4 to the negative 3 power equals 1 over 64. If you remember rules of exponents, negative exponents put things in the denominator. So this is a true statement as it stands. I'm going to write log. Here's my base. The exponent is negative 3. And that goes over here. And the argument, 1 over 64. I might want to put some parentheses in there just to make it a little bit more clear. And again, the exact same information, just looks a little bit different in form. If we can do that, we can also rewrite logarithmic statements as exponential ones. And that's pretty useful, especially here at the beginning when logarithms aren't so familiar and we know a lot more about exponential functions than we do about logarithms. I'm going to notice log base 2. So there's my base. In a logarithmic statement, the exponent is over here. So I have 2 to the 5th power equals the third number. And when you're finished, this should be true. So I should be able to look at 2 to the 5th power equals 32 and go, let's see, 2, 4, 8, 16, 32. Use your fingers if you have to. Yeah, that's true. 2 to the 5th power is 32. So I did it right. If I took log base 2 of 32 equals 5 and came up with 5 squared equals 32, that's not true. And it should be true when you're done. So it's a little quick check. And then let's see. I have log base 8. And if you read it that way, log base 8, you've kind of told yourself already what the base is. Log base 8 of 2 equals 1/3. My exponent is 1/3. And 2 is my other number over here. And so rules of exponents again. Fractional powers are roots. So 8 to the 1/3 power, which is totally different from 8 to the 3rd power. 8 to the 1/3 power is the third root of 8, the cube root of 8, which is indeed true. 2. So that's a true statement. You don't need both of those. One or the other will do. So to summarize here, the inverse of the exponential function base A is the logarithmic function base A. Any exponential statement we can write in its logarithmic form. Any logarithmic statement we can rewrite in its exponential form.